Welcome, everyone. I'm genuinely excited to be here, part of an international conference. So welcome from wherever you are in the world. My name is Bowie Owens, and I'll be talking this morning about bringing existing code to CUDA using constexpr and stdpmr. So let's begin. So to get started, I thought I'd share my plan for the talk this morning with you, and I want to get started with some introductory comments that will explain some context about who I am, what I've done, and who I think this talk will be helpful for. Then we'll look at bringing existing code to CUDA in two major sections. First, relating to do with memory, and then second, to do with host versus device functions. So if this terminology is not familiar, I'm going to try and explain the terminology that I use as I go along, so don't be too worried. And also, at the end of each section, I put in reminders to me to try and address the questions within that are raised during the talk. So if you have questions, please use the Q&A feature rather than the chat or putting your hand up, and I'll try and address those as we have time and as I get to them. Okay. Now, also, I'll just mention I have inserted the slide number in the lower left corner. You might want to make use of that if your question relates to a specific slide to make it easy to find later. Okay. So let's move into that introduction. My name is Bowie, as I said. I work at a government-funded research organisation in Australia. It's actually 7 a.m. in the morning right now where I am. And the team that I'm part of is called Risk Lab, and we use applied mathematics for developing software for managing financial risk. Now, the team that I work in is a relatively small team, and that's great for me because it means I get to touch lots of different facets of software development. And one of the things that I've been doing as part of my work recently has been accelerating some of our existing software using CUDA, and making our software go faster is actually one of the things that I really enjoy getting the opportunity to do. And so I wanted to document my experience or some of the things that I'd learned along the way, while it was still relatively fresh in my mind, and also because I hope that it would be of use to people who are in a similar situation, who have existing code and think that it might be a good fit for doing calculations on the GPU, and but haven't started on that process yet. Okay, so with that out of the way, let's look at what you see when you start on learning to use CUDA. Well, let's look at one of the really simple examples that you might find and how to bring that to CUDA to begin with. Okay, so this example here is taken from a post on the Nvidia website entitled An Even Easier Introduction to CUDA. So this is the starting point, the CPU-only version. That's about as simple as an example as we can get. We are going to set up, you can see in the code, we set up two vectors, X and Y. We fill them with some values, and then we use a function to add them together, and then we clean up after ourselves. Okay, so that's the starting point. Let's look at how we bring this simple code over to using CUDA for calculations. Okay, so step one is that we need to allocate memory in a way that's accessible to the GPU. Not all memory is accessible to the GPU, but what CUDA refers to as unified memory makes it relatively easy by providing a single memory space accessible to all the GPUs and CPUs in your system. And to allocate memory within that space, you call CUDA malloc managed, which returns a pointer that you can use on both the CPU and the GPU. And to free the data when you're done with it, you call CUDA free. Okay, step two. we have to turn our function into one that the GPU can run. It's not every function in your program will be accessible to the GPU. So we have to mark them for special treatment. In CUDA, this kind of function is called a kernel function. And to make our code into a function into a kernel function, all we do is add the specifier at the front, global. Now, there's a lot of underscores, so I'm going to treat them as silent in my pronunciation. So we put the specifier global in front of our add function. Okay, that's the second step. Now, the third step is that we need to launch the kernel, which invokes it on the GPU. CUDA launches specified using this extension, this triple angle bracket syntax, and then sets up the call to the add function, but executes it on the GPU. Now, briefly, I wanted to touch on the parameters that go inside those triple angle brackets. Now, roughly speaking, when you multiply the two numbers together, that gives you the number of threads that are going to execute the kernel function in parallel. And by choosing 1, 1, I have set this up to only use a single thread. And that's, as a result, it's only going to use the tiniest available fraction of the GPU's hardware. To fully utilize it at the GPU, you want to spawn many threads and divide the work up between them. But this makes the examples that I'm covering today a fair bit more verbose. And I wanted to focus on things that I thought there was a more challenge in scaling when you go from the simple examples to complicated ones. And I thought the process of doing this division of work is relatively straightforward. Okay. So we're not going, that's one of, since I only have an hour, it's one of several things that I'd love to talk about, but to focus on other things I'm going to leave out for the time being. Okay. So let's, to bring it all together, here's the complete example with all the changes to get this code to execute on the GPU instead of on the CPU. Now, this example is an excellent starting point, but its simplicity conceals a number of issues that present themselves when you try to apply the principles to existing code, when you've got a substantial amount of real code already and you want to use these principles in your program. So next I'm going to talk about memory allocation, and I see I already have one question to do with memory allocation. That's excellent, and I am going to cover that during the next section. But first, if there are any questions about this introductory example, let's get those out of the way, and then I'll move on to the memory allocation. Well, it does seem like there aren't any questions yet about the introductory example, so let's keep moving. So I thought maybe someone would ask about the kernel parameters, but so there was some very quick slides in there. You might freeze frame later if you're watching later to address those. Okay, so memory. Let's start with, why is there a challenge with memory at all? Okay, so taken from the Nvidia website, it notes that the memories of the CPU and GPU are physically distinct and separated by a PCI bus. So the GPU cannot directly access the system memory, nor can the CPU directly access the GPU memory. So we have this physical separation. So we saw the solution earlier in the example taken from the simple example, which is using unified memory. Okay. Now, so what is unified memory? This will help us a little with the question that we're going to address soon. Unified memory creates a pool of managed memory that can be shared between the CPU and GPU. Now, the managed memory is accessible to both the CPU and GPU using a single pointer. So let's go back to that simple example and revisit how the memory is allocated. Okay, so here we have side by side the allocation that we had in the introductory example and the allocation that we do in the GPU example. So the blog post tells us all that we need to do is replace the calls to new with calls to CUDA Malloc managed, and replace calls to delete with calls to CUDA free. Okay, so this is the first example of a challenge for an existing code base. Because in an existing code base, it's unlikely that your memory allocation is being done by raw new and delete statements that you can go in and change. Okay. It's far more likely, sorry, my slides didn't progress the way I expected there for a second. Okay, it's far more likely that you're managing your memory by a type that conceals the allocation and deallocation of memory. So as an example, we're going to use standard vector. Vectors are, of course, a good choice for when you're working with a GPU. GPUs love vectors and matrices and things that are of that form. So the question then becomes, how do you replace the calls to new and delete in this code? And okay, so the approach that I took, or the mechanism that we have for controlling the allocation of memory for containers in C++17 onwards, is to use standard PMR, which was added in C++17. We had added to the standard a number of new types, including standard PMR memory resource, standard PMR polymorphic allocator, standard PMR vector, and standard PMR monotonic buffer resource. So we're going to look at how we can use these tools to control the memory allocation using something for standard, essentially for standard vector. Now, if you don't have access to standard PMR, since I had access to standard PMR in C++17, I didn't investigate pre-C++17 style allocators. So if you don't have access to standard PMR, you could be, as I understand it, the same principles will apply, but the syntax and how you set up the allocators will be different. Okay, so let's look at how we can use standard PMR to control the memory allocation. Okay, so standard PMR allows us to control memory allocations by constructing a memory resource object. This object will handle the allocation and deallocation of memory. And what we do is we construct an object, and then we are going to pass that object to the constructors of the vectors, which will use that object to allocate memory within the unified memory space. And as a result, the elements of the vectors will then be accessible to both the CPU and GPU. Okay, so this is what so what does this memory resource, unified memory resource type look like? Let's look at its implementation. Okay, so it's going to be a class or a struct that inherits from standard PMR memory resource, so that it can implement the memory resource interface. Polymorphic means we're going to be using lots of classes and virtual functions. So the virtual functions that the class, the unified memory resource, needs to implement are an allocate function, a deallocate function, and inequality comparison. So we're going to focus just on the allocate and deallocate. So let's look at what their implementation looks like. Okay. So to implement the allocation and deallocation, this is where we are able to use call CUDA Malloc managed to do the allocation, and also then CUDA free to do the deallocation. I see someone has raised their hand. If you could, I'd encourage you, if you have a question, if you could please use the Q&A feature. It's a bit tricky for me keeping an eye on the chat and everything at the same time. So that's, thank you. Okay, so it's relatively straightforward. We just delegate allocate to CUDA Malloc managed and CUDA free, okay, to do the deallocation. There's a couple of simplifications that I've made here. First, I've assumed that the memory is suitably aligned. So I'm ignoring there's an alignment parameter on the allocation. And the second simplification is I'm going to assume that the caller will always deallocate all the memory that they have allocated so that they are responsible for avoiding any leaks of memory. And of course, in there, if something goes wrong, then we throw a bad alloc to indicate failure. So let's revisit that recent example and talk about what this means now. Okay, so going back to the overview, we have our UnifiedMemory Resource object. It's going to be passed into the constructors in the vector. Now we have replaced our calls to new and delete with calls to CUDA Malloc managed and CUDA free. So the elements of the vector are going to be accessible both to the CPU and GPU, but the objects themselves, X and Y, are going to be allocated on the stack. And that means that the objects themselves are inaccessible to the GPU. So there's something that we want to avoid. Okay, so if our objects are allocated on the stack instead of unified memory, we need to avoid passing the object itself to the kernel functions. So in the example on the left, it's fine for the CPU to receive X and Y when adding them together by reference, but on the GPU, this will be problematic. So what we can do is instead of passing them by reference, we can convert them to some kind of spanning type, or perhaps even just a bare pointer, and pass that by value. Then there will be no references to the objects that are located on the stack. In general, copy by value parameters helps you avoid this issue of passing in references, but you still need to be careful and we'll look at what you need to be careful of next. There we go. So, like I said, in general, copying by value will help you avoid this issue, but you need to be careful to avoid concealing references to other objects within the objects that you are copying. So in the code that I work on, we have a lot of expression templates. And so we end up with these callable objects, like we see in this example at the top, where we pass in an object or function that abstracts a more complicated expression behind the scenes. So in this particular example, we're doing an addition of two vectors behind the scenes. Now, naturally, you might want to structure these sorts of types to hold references to the vectors that they're going to be working over. But even though you're passing the callable object f by value, because it contains references to other vectors, these might be in memory that's inaccessible to the GPU. So you can apply the same technique by changing the data members of your types to avoid this problem. Now, hopefully, the thing is, hopefully, if your data members are suitably protected, then this won't have too many impacts on your wider code, because one of the reasons you're wanting to avoid when you've got lots of code is to avoid changing types that are used all over the place. Okay. Okay, so now that we've looked at using unified memory to do our allocation and solve our access problem, we've just gotten one question that relates to this slide. Shouldn't the operator, the callable operator on the add functions be marked as device? The answer is, I'll come back to, yes, at the moment, these are missing the specifiers that you would need to make this available to the GPU properly. This is CPU-only code at the moment. But yes, good point. Normally, you would need to mark these as host versus device. I did want to focus more on that side of things in the second part of the talk, which is why I thought I'd get away with omitting it. But that's a good pickup, Dennis. Thank you. Okay, so where was it? We want to consider whether we always want to use unified memory. And this is going to address the question from, and we'll get into the question from one of our attendees about the different memory allocation functions that we can use. Okay, so let's revisit that explanation of unified memory. And so unified memory allows you to pretend that there's no separation of CPU and GPU memory. It doesn't remove that separation. What it does is it performs an allocation both in the system memory and in the GPU memory. And then, as we see from the Nvidia website, the system automatically migrates the data allocated in unified memory between the host or the CPU and the device, the GPU. Okay, so is there a reason why you would want to avoid unified memory? Well, the synchronizing of values between the system and the GPU memory can negatively affect performance. To get the best performance, you want to avoid alternating between host and device calculations between CPU and GPU. And using memory accessible only to the device makes it very clear if you've not successfully limited your calculations to the device. Okay, so it's easy to define a PMR memory resource that allocates memory accessible only to the device. So let's look at how to do that. And it's going to look very similar to the example we looked at before. So we're going to, we define a new type, a new memory resource. This time I've called it device memory resource. And it has to, of course, inherit from the same class and implement the same functions as before. Okay, but this time we're going to use CUDA Malloc to allocate memory. And now our question was, what is the difference between CUDA Malloc and CUDA Malloc managed? Okay, so the difference is that CUDA Malloc managed will allocate memory in the unified memory space. It will allow the CPU to access it and the GPU, and it will automatically set up transfers between the two memory, the memory on the CPU, the memory on the GPU. Okay. CUDA Malloc will only allocate memory on the device, on the GPU. The memory allocated there will be inaccessible to the CPU. Okay. And of course, there will therefore be no scheduled transfers between the two parts of memory because you've only allocated on one side. Now, I hope that addresses the question on the difference between CUDA Malloc and CUDA Malloc managed. Okay. So now making use of this memory resource, very similar to what we saw before, we're going to instantiate an object of our new type, device memory resource, similarly pass it to the constructors of the vectors. But the important difference now is, sorry, we just had another question come in, which it's a good question, so I will endeavor to get to it. Okay, so now the important difference here is that the elements of the vectors are going to be allocated in memory that is accessible only on the device, the GPU. And as a result, this example is actually going to fail if we try and execute it. So the question is, why doesn't this example work? Okay, so the reason why it doesn't work as is because the constructor for the vector objects will use the standard PMR polymorphic allocator behind the scenes to default construct all of the elements of the vectors, setting them to 0. And this is going to be done on the CPU. And of course, the second that the CPU tries to default construct the memory, it's going to fail because it's inaccessible to the CPU. So how do we avoid that? How do we avoid that problem? There is a solution. And there we go. So what we need to do to work around this problem is to create an allocator that is going to default initialize the primitive types when asked to construct them. So it's not going to set them to 0. It's just going to essentially do nothing. So the easy way to do this is to reuse most of standard PMR polymorphic allocator, which is what the standard PMR vector is using behind the scenes. But what we do is we replace the construct function with one of our own that will use the placement new operator, but without any additional arguments. So this is going to default initialize primitive types and therefore not write to them during their initialization. Okay. And so to make our lives easy, we're going to copy the pattern that actually the standard library uses, and we're going to introduce an alias so that we don't have to repeatedly mention the name of the allocator, because then it gets to be a lot of typing very quickly. So let's go back to that recent example and consider how this helps. Okay. So now I've taken away the standard PMR from the front of vector. We're using our own allocator instead, and what's going to happen is that we're going to therefore not initialize any of the elements. Okay. Now, and as a result, the constructor calls for the vectors are not going to touch any of the memory elements. Okay. So there's a question from Paul, thank you, about why not just an empty function? Preceding slide. So this will be properly behaved in the case of U not being a primitive type. So if it is a class, so then it will be properly behaved, is the main reason. I was also concerned that around if undefined behavior, if you don't officially bless the primitive type, the memory as a primitive type, but I'm worried that that might be a little bit of a superstition on my part. But this, the important detail is that using the placement new operator will construct the type. If it's a non-primitive type and it does have a constructor, it needs to be constructed properly. Okay. So the question was, why not just create memory on a device? To interact with the classes that you potentially already have in place. So in our code, we were using standard vector in places, and to control the allocations there, you have to go through something that looks like an allocator. You have to create an allocator type like this one, which you then, you can see we're using the original standard vector in our alias, so that we're just redefining or defining our own allocator type. So I hope that answers your question. Mark off some of those. Okay, so what we've done is we've defined an allocator. Hopefully mine is correct and not, and we have now adjusted our vector to use this allocator without changing substantial amount of code, and now we no longer initialize the memory on the CPU. Okay, so let's say we've done some more reading on memory resources and allocators. We've watched some videos on YouTube by, say, Alistair Meredith or Pablo Halpern, and we get excited about using more of standard PMR. Can we go on our way using standard PMR without any further excitement or any problems? Oh, sorry, sorry, not sure what happened there. That's the slide I want to be on now. Okay, so let's say, like I said, we've watched some videos. We've learned about monotonic buffer resource, which pre-allocates memory and then very efficiently parcels it out as required, and then cleans up after itself nice and quickly. So we want to use that. So unfortunately, this example is also going to fail for reasonable implementations of the standard library. Okay, now why doesn't this work? Okay, so typically the memory resource objects provided by the standard, they make a promise that they will actually clean up all the memory that you ever allocate with them. It's a really helpful feature, but it does mean that they store bookkeeping information so that they can clean up properly, so that they can do that. And the bookkeeping information is usually placed in memory that is allocated by the upstream memory resource. So in this case, our monotonic buffer resource chunk is going to keep its bookkeeping information in memory allocated by the device memory resource. And so again, when the CPU touches this memory, the program will fail. So since it's hard to know exactly what the standard memory resources will do, I've shied away from using them in combination with device memory resources. Instead, I've written some memory resources that allocate their bookkeeping information using new and delete instead of the upstream resource. And so that the writing memory resources is fairly straightforward and can be quite useful to take advantage of structure that you have in your program. Okay, so one of the questions I have is, would having different types of allocators in the interfaces help you avoid errors accessing memory from the wrong device? And the answer is yes. You can take advantage of the type system to then make sure that you're doing the right thing. So often the memory resources get passed around by their base pointer, but you can also pass them around by pointer to their final type. And then you can use the final type, whether it's a device memory resource or a unified memory resource, or one of the memory resources that will allocate on the CPU. And you can overload functions or use type checks to then do the right thing for the memory resource, knowing where the memory is going to be coming from. But that's if you can retain access to the final type of the memory resource. You need to be able to do that. So as soon as you pass in a base class pointer, then you've lost access to that information. But it is possible. In certain cases, it is possible. That answers your question. Yeah. So let's wrap this up with one final example, and it touches a little bit on the question I was just trying to address as well. So tying it together, you're probably going to want to use unified memory, a memory resource that allocates unified memory, if you're not sure what's going to be done with the resource. So this is particularly useful for objects that are going to be allocated in one part of your system that you want to keep essentially oblivious to the fact that you're using CUDA. So in this case, my example is I've hidden the construction of the x vector inside a function getX. Okay, now we can assume that this may know nothing about us using CUDA. And so we can, by passing in a unified memory resource, the memory allocated will be fine for many things. Okay. Whereas we may choose to use device-only memory if we have complete control over how the memory resource is going to be used, and we want to eliminate the possibility of operations on that memory occurring in the CPU to ensure that we're getting the best possible performance. Okay, so that was memory allocation. Next, I want to talk about the differences between host and device functions and what that means for existing code. But I'll just give us a little bit more time. If there's any further questions about memory allocation, I'll address them before we move on. I think that we're good. So let's talk about host versus device functions. And it's excellent. I see we've already got some people in the audience who know a bit about this, but let's start by clarifying what are host and device functions and what purpose do they serve and how do we set them up. Okay, so going back to our original blog post that I was quoting from, it says that we have to turn our add function into a function that the GPU can run called a kernel. Now, it said all we have to do is add the specifier global to the function, and this turns it into a kernel function. So not all of our functions can be accessible by the GPU, so we need to mark them so that they will be given special treatment. They will be compiled in such a way that the GPU can access them. So an important detail with all of these specifiers, and we're going to look at two more, is that they control where the function can be executed where the function can be called and where it will be executed. And these are quite important details for existing code because you've probably got a substantial amount of work that you've already done. You don't want to have to duplicate your logic, your code, to run it on the GPU, and you don't want to lose it either. You don't want to give up the calculation on the CPU. You want to complement it. You want to do the same thing in both places with the minimal amount of duplication of code. Okay, so we have so to do this, CUDA gives you 3 execution space specifiers that lets us do this, lets us organize our code naturally and make functions available both to the host, the CPU, and the device, the GPU. Okay, so the specifier we've seen so far is global, declares a function to be a kernel function according to the CUDA terminology. Now, I said those important details around these execution space specifiers are where it can be called and where it will then be executed. So the global specifier indicates that the function is executed on the device, but callable from the host. So you call it on the CPU, executes on the GPU. Now, the second specifier, which someone asked about earlier, is the device execution space specifier. It declares a function that is executed on the device, but is only callable from the device, which means that it needs to be called either from a global function that started the chain or from another indirectly through another device function. Now, the third of the execution space specifiers is host. Host means that it is executed on the host, the CPU, and callable from the host only. Okay. Now, if we omit host as a specifier from any of our functions, which is how your code is going to start when you've got existing code, it's going to be callable from the host only. The host will be assumed. So what this means is that we can take the logic that I had duplicated earlier in the examples and place that into a function that to be reused. So the first thing is we note that it's permissible to use both host and device specifiers together. This will mark the code to be compiled both as accessible to the CPU and a version accessible to the GPU, so that we can call it from our function that's going to do our work on the CPU and our global or kernel function that is going to then start the chain of execution on the GPU. Okay, so what I wanted to focus on, bring your attention to, is of course this kind of annotation, device annotation, it is viral. To execute on the device, all the functions called within a device function must also be annotated as device. So what happens is, this is, describe it as an inconvenience for your own code. You have to go through and mark your functions as device, but there's a bigger problem. So what's the problem here? So the problem that we have is that standard array, which I want to be able to add, essentially, I've got sort of two matrices now, and I've used standard array as my row type, essentially. So the problem, what's the problem? The problem is that standard array is a class. And so indexing into it is now a function call. If we try to annotate our add function as host and device, it's going to fail because we're calling host-only functions, the member functions of standard array. Now, and generally speaking, you may not be able to alter the definitions of the libraries that you're already using to add host and device. And okay, so I've got some questions come through. The first from Alex. So without using the block ID and thread ID, isn't this loop going to work on each GPU thread? The answer is yes, but remember earlier I said I was cheating. To make my example simple, I'm only going to use one thread. And we can talk about, maybe later I can, if there's time, I can revisit how you do the division of work. But at the moment, I'm cheating and assuming there's only one thread. But good pickup, Alex, thank you. Okay, so there are a couple of solutions to this problem, that you have libraries that you might not be able to change. And there's two solutions to your problem. The first, the least desirable, is that you would rewrite all of your code to not use any third-party libraries. That you would, and then you would obtain complete control over everything. Okay. The second is to switch to libraries that are CUDA aware. Now, Dennis has asked some questions about that. He's brought that up. CUDA comes with a substantial fraction of the standard library that you can make use of. The other thing they also provide is Nvidia a Thrust, a library they call Thrust, which provides a number of useful features. Now, I went with a different approach because I wanted to modify the least amount of code possible. I wanted to contain the changes to the smallest region and to not alter data structures that were used throughout the code. Because the problem we have in existing code typically is that you have the objects that you use are not necessarily limited to a small area. They may form part of the interface or contract between different parts of your system, and you want to keep those other parts of the system as you may need to work incrementally, modifying only part of your system. So yes, Nvidia ships a standard library. They also give you thrust, and those might be great solutions in your circumstances, and especially if you're starting from scratch, they're probably good. They're good solutions. But I went with a third approach, which is where constexpr comes in. Okay, so there is a flag on the Nvidia compiler that's difficult to pronounce. But what it does is it allows you to treat constexpr functions as if they had been annotated as host and device. So I've got the link there to the documentation on that for people who want to look at it later. Okay. And of course, it's an experimental flag. Behavior may change. Okay. So what does that mean for our examples? So going back to our simpler example, instead of going through and marking our backend add function as host and device, we can mark it as constexpr. Okay, so this is nice for our simple example. And let's go back to that slightly more complicated example with standard array. So what this means is by enabling this flag, we can call any other constexpr function within our own constexpr add. And the good news, in my case, was the operator, the square brackets, the indexing operator on standard array is constexpr in C++ 17. So now this example is good. We've solved the problem without changing any of the types involved. So we continue to use exactly the same library and implementation and types that we were using before. Okay, which is a nice property when you have existing code. Okay. So admittedly though, we haven't solved the problem in general, but rather we've traded one annotation, one specifier, host device, for another. So we've replaced them with constexpr. So the thing is, though, constexpr, of course, has a really big advantage. So because constexpr serves its own useful purpose, so there's enthusiasm for adding constexpr to functions, and this includes adding constexpr to functions in the standard library. So I'm referencing the excellent talk by Jason Turner and Ben Dean here as an example of that enthusiasm for constexpr, all the things. Okay, so we'll reflect on why that. Oh, sorry, we've just gotten a question that relates to this slide. Can we now directly use the constexpr add instead of add CPU? And here, this is actually where my my omitting the details for the division of work have let me down. So yes, you'll notice that they actually the constexpr add and is exactly the same, does exactly the same work as add CPU. There's no important difference there. The difference starts to come in when you start doing division of work. So the add CPU will need to, you typically add parameters to the add function that will let the individual functions do only a fraction of the elements. When you do the work on the CPU, you set up those parameters so that you do all the work. You touch all the elements. On the GPU, you touch only a fraction. I think I'm running out. I'll see if I can come back to that for you a little bit later, Alexander. Or maybe there is an opportunity for us to chat afterwards in the GatherTown community. So, but yeah. Okay, so what does that mean for us? What it means is that it opens up a substantial fraction of a number of important libraries. For me, what were important were the standard library. We use standard array in a number of places. And that's in C++17, that's constexpr friendly. Also, the GSL guideline support library, its implementation of span, because span is not standardized in C++17, has been incredibly useful for us. And its functions are likewise marked as constexpr. So I've kept this list short because I didn't want to comment on libraries I haven't used myself, but I would hope that in the audience, you'd be thinking about libraries that you use and their support for constexpr, because I'm sure there's plenty more to add to this list. The other thing is, like I said, because the constexpr serves a useful purpose, if the library that you're using is not already using constexpr, they may be willing to accept patches to make it so. Okay. Alex has asked, can with C++20 we just use standard span? And I believe the answer to that is yes, as long as the member functions are marked constexpr, which I believe they are. But for me, on C++17 for a couple of reasons. So that's where I get span from, is the GSL library. But yes. Okay. And so, as I was saying, that not changing things saves you time. It's easier for a couple of different reasons. You don't have to invest any work at that time, but also, there we go. So no work is a lot less work than some work. So you've already got your existing code and you've tested it, you know it works. The fewer details, the fewer lines that you change, the less that you're going to need to test and debug. And you do have to, of course, test that your code is appropriately marked constexpr. You can do that by adding tests that execute at compile time, and will terminate the compilation with a failure if the test fails. This is going to ensure that you do not call any non-constexpr functions from your constexpr functions. And it also is going to give you a place to verify that your behavior is correct both at compile time and runtime, as they can diverge. And now we've got a question from Leslie Lai. I think that the NVCC, the Nvidia compiler, doesn't support C++20 yet. That's certainly the case with the version of in the Nvidia compiler that I've been working with on Linux. I didn't want to say that just in case they've released something that I'm not familiar with. But I was under the impression that's the version that I've been working with because of the version of the compilers that I have available to me. So thank you, Leslie. Okay. So yes. Okay. So not changing things makes our life easier, both in terms of not having to do work, but then also not having to follow, not creating changes that need to be properly tested and worked through. Okay, which is, depending on how big your code base is, this could is potentially a really important factor. Okay. So next, I'm going to talk quite briefly about return on investment. I was going to talk about benchmarking, but time was limited, and also it was pointed out to me that the benchmarking I do on my code is not going to be necessarily that helpful, since it is proprietary and the details of it are specific to ourselves, or our team and our clients. So unless there's any last-minute questions about the constexpr and execution space specifiers, so I'm going to move on to the next and final section of the talk, return on investment. Okay. Sorry, went the wrong way there for a second. Okay, standard PMR allows you to control the allocation of memory, which is necessary for access by the GPU. So you have to adjust your memory allocation. Now, the good thing is that using standard PMR may allow you to reduce the number of calls to the allocator or improve the locality of objects in memory by using those intermediate memory resources like monotonic buffer resource. And this may improve the performance of your code. It also standard PMR gives you a way to instrument your code and identify inefficiencies. And I can assure you, if you add a print statement to every time you allocate some memory, you get pretty motivated pretty quickly to eliminate those copies of objects that you didn't realize were there. Now, the downside is this requires your standard library to support standard PMR. Now, unfortunately, I believe it's libc++, the Clang standard library, is falling behind in standard PMR implementation, and you require C++ 17 or later. Okay, so, and moving on, constexpr. So it's necessary, well, it's a useful approach to expanding the set of functions available to the GPU in tandem with that flag for the compiler. Including expanding functions, the availability of functions in third-party libraries that you might not control. Now, it too may improve the, investing in using constexpr may also improve the performance of your code. Two possibilities include moving work that you are doing at runtime to compile time. And the other thing, we haven't, in our experience, I didn't see as much benefit from this, but one thing that we see more opportunities in our code is and the calculations that construct the dimensions of vectors and matrices may be moved to compile time. So things that were had a runtime dimension can be known, their dimension can be known at compile time. So I'd like to do more work with that. Okay. So we're doing pretty well on time. I've spent most of it talking about things that are not necessarily specific to CUDA, so standard PMR and constexpr. I actually see this as an incredibly positive thing. I hope you do too, because it means, what this means is that you can pave the way in your existing code for using CUDA by taking steps that each individually have their own merit. So as we saw, adjusting code to use standard PMR and using constexpr has its own value in and of itself. So often in real life, when you're working on a project and improving performance may be only one part of your job, it may be possible that you become interrupted and need to work on something of higher priority before you can achieve the substantial benefit from CUDA. But what this means is that each of the steps that you take along the way to get there actually have some worth in and of themselves. So if you become interrupted, then the time is not wasted. Okay. So we have only a very short amount of time left. If there are any further questions, I see that the queue is empty at the moment. I can address them really quickly. Also, I will shortly be joining the GatherTown venue to follow up with discussion. I'd be happy to talk to you there and address further questions in that venue rather than this one. Okay, so we've just had a question about static analyzers. I don't believe that static analyzers will help. I'm not aware of any, and I believe that because you're doing a lot of work through virtual functions, the properties are necessarily only going to be known at runtime, but that would be great if someone wanted to write a static analyzer that would detect these kind of memory problems for us more readily. And as I said, if you retain the final type of the memory resource, you can do some checking based on that. but only if you retain the final type.